Alrighty, I think we are live, the second episode of How Things Work. So before we get started, I just wanted to read a quick disclaimer here. So the podcast is for informational purposes only. Nothing said on how things work should be interpreted as an offer to buy or sell securities, financial advice, legal advice, or as an opinion of the employers at which our guests work. Lastly, our guests and I may hold positions in the companies or projects discussed. Usually these people are founders, so they probably do. So with that, how things work. So the quick intro, if you haven't heard of us before, is many podcasts geared towards a non-technical audience and focus on the impact, but stay away from the nuanced technical conversation about how things actually work and how mechanisms are actually brought to production. And so today I'm really excited to host Shresth from the Pod Network and to discuss their latest work around partially ordered datasets. Welcome.
Thanks, Patrick, for inviting me here and being on the second podcast. I'm Shresth. I'm the CEO of Pod and been a builder in the space for quite some years. Started into smart contracts and auditing, and then got interested in the cryptography and consensus. And it's been a fun ride. And now we're quite excited with what we're building with Pod. It's a new paradigm of building decentralized systems, which is not blockchains. It doesn't have any blocks or chains, and that's kind of the fun of it. And excited to tell more about it.
Yeah, I think naturally the first episode was about ZK related stuff, and then the next one's consensus and like not consensus maybe, and then the next one will be about storage. So we're just kind of running through the gauntlet here of different things. I was really excited to have you guys on because my first love in crypto when I first kind of got interested was this notion of like how you kind of do these like consensus-less things, or like if you have these like kind of different views around agreement and everything like that. And it seemed great for payments, right? Like kind of all these different applications that you could fit into this world where you didn't need a total order over everything that was going on. I'm really curious, maybe just to get things started, where'd this come from? Like, what was the motivation to dig into this work? And like, maybe you just kind of woke up one morning and you're like, perfect, partially ordered data sets. But usually there's a backstory here.
Let me give you a little bit of the backstory. So, I was working at Common Prefix, and this company spinned out of Common Prefix. So Common Prefix is a science-based consulting firm, and we've been working with a lot of great projects, very blockchain natives on the research side, things like Babylon, Axelar, Celestia. And one of the projects we were working with was flashbots. And we were looking into how to decentralize the Suave auction layer, right? So if you guys are familiar with the whole MEV system, right? The proposer-builder separation is a two-sided marketplace. And there is builders who are kind of bidding, saying, I want to be the next, I want my block to go to the next block. And then there is this relayer doing auctions. And then the proposer takes this thing and gets extra rewards. And, it kind of democratizes the MEV, what the tagline that they have. And
the whole pitch with the new system, to be clear, is like it's all in like TEEs, like you can kind of send transactions in, and or is this a precursor to that?
I'm talking about the current system, which is centralized without TEEs, right? And then you want to go to Suave, which is you want to make this decentralized. And there's like doing auctions decentralized. There's two parts to it, as I see it. One is how do you do this kind of execution of auction, right? Like how do you take the bid set and then calculate the maximum bid, and that is what you can run inside the TE. But then even before that, you have something which is more peer-to-peer and distributed, which is how do you collect the set of bids?
You got to agree on the bid set first, I guess.
Yeah. Exactly. You need some kind of way to say, okay, this is my bid set, and then you want to make sure that you don't censor some bids. You want some kind of guarantees on censorship resistance. And censorship resistance is not a very well-defined term. People have economic definitions. People question why is it different than liveness and so on. So basically, we were working through Common Prefix on this thing. It was a kind of a grant/project together where how do you actually build a decentralized auction layer? And we came up with this very simple kind of timestamping protocol that was inspired by the certificate transparency of Google, right? Where it's just like a bunch of validators that are just keep signing, right? And we looked at the protocol and it looked too simple. It looked like there should be something that's kind of broken about this. Like, it doesn't do any kind of lot of rounds of communication. It's very simple and kind of works and does provide the censorship resistance properties that you need. And then we started.
Can you pause for 1 second before you get in that?
Yes.
So like with basically the idea around censorship resistance here, just to clarify, is the idea that if I'm some random person that wants to send some transaction at a certain price, that I can make sure that everyone gets it and gets it by some latency or like within some duration. Is that the operating definition you guys have been going from?
So the definition is approximately there. Like, so the definition we had was if you censor the transaction, or if you like essentially if you try to include a transaction and your transaction is not included within a certain delay, then the whole system stalls. So you cannot move the system without by stopping one transaction to enter, right? And that's kind of the Byzantine definition. It's different from liveness because liveness only talks about a single transaction. If you send a single transaction to enough parties, then this transaction will make in, but it doesn't talk about every transaction. And so kind of, you cannot selectively include some transaction.
Got it. Is the lead. All right. Sorry to interrupt you. I just wanted to make sure we got that.
Keep interrupting so that we make sure that the audience understands the nuances, because I might just kind of go over things.
Go off. Yeah. So certificate transparency of Google. Where were we going?
So we took inspiration there, and we just built this thing, and we proposed to them, and we kind of stepped back and started thinking about what can you do with such a system, right? Like where you do not have the full consensus and you have some kind of set-like properties. And then, of course, there's the whole line of work with fast-paced sui luteris, which is done by Miston Labs and their scientists, which is amazing. And there's more recent work with Stingray. And then there is also a line of work by the Rogers group in Switzerland with consensus number of ABC and so on. And these were protocols essentially, which were relaxing the consensus requirements while still being able to do fast payments, still being able to provide execution on CRDTs or ownable objects. And we will go on in depth about that. And we kind of took all of those components, combined it together, and then started building something more on top. And we realized that you can do a lot that blockchains are doing today without needing to pay for the cost of global synchronization, which is very expensive. That's where the vision came. And because we have scientists who are super opinionated and have been in the space for so long, they were they really liked it. They were okay, this is too simple, and let's just kind of see where it goes. And that's how the whole partially ordered data set came to be. So it was really inspired from the whole MVP pipeline, but then this kind of started building on around.
So you guys at Common Prefix, I think you mentioned, so you're working on this project for Flashbots, and the idea is that some mechanism falls out of this, and you're this could be a standalone mechanism that can kind of be used more broadly, and that's where the partially ordered data sets come from. Got it. And so I guess the obvious transition point there is so you mentioned a few other mechanisms I'm familiar with, at least the SUI work and Miston Labs work around, I think they call it FastPay. I don't know. There's been iterations of the naming scheme there. Maybe you could talk a bit about how you go from something like that, maybe explain a little bit about what's going on there, into what you guys are doing, or what the big leap was, or that you feel like you guys are making.
We should make some distinction on what's already out as SUI in production versus what's on the paper. And what
great idea.
A lot of differences. Also, what's on the part paper and what we're implementing has some differences. We're trying to get it closer and closer, but it's going to be
the classic dilemma. I think I was joking at some point that at least when we were at Avalanche, I'm not even sure any of the paper, much of the paper is even in production anymore. So the thing is, these projects evolve. They respond to engineering challenges, and they introduce new mechanisms. So it'd be great to start there, because I think people sometimes don't have an appreciation for these things are alive, and you see data and you adjust.
I really appreciate the whole Miston Labs and SUI team. We know them very well. We've been working with them through Common Prefix, and we know the scientists and everybody. So it's a great team, and a lot of good work they've done with Libra originally, and then later on with Miston, right? So the FastPay paper is an extremely simple construction, right? And it just does 1.5 rounds of communication, and you can do fast payments. And if you take a step back and you think about Bitcoin, right? Like Bitcoin started with, can you do peer-to-peer payments? And it proposed this amazing system, very complex with the whole proof of work. Now somehow Fastpay is saying you can do all of that, but like in a very, very simple approach. Of course, it doesn't have open participation yet, and we can talk how to build that on top. But everything else, the peer-to-peer communication part and having Byzantine resilience, you still have that, right? And it's very simple. So it kind of begs you the question of what else can you do? And then the sui luteris, which was kind of a natural extension, what it said was, okay, we can, it's not just limited to it being payments, but you can actually do everything which is owned by a single user. So there is only a single writer styled object. So there's only one person that can modify an object at a single time. And then it also said eventually everything will go through consensus. Eventually everything will pay the price of consensus. So there is a subset of the things which will get a finality fast, which will get a certificate saying this is final fast. But then eventually everything is totally ordered through their DAG-based stuff, and then you use the consensus for reordering and so on, right?
Yeah. And the idea there, right, is like it's the whole notion that where like you're fundamentally these things, a lot of them are at least trying to prevent the ability for you to pay two people. And so like what are you trying to do here, right? And so at least in my understanding of that work is you have some object, you make sure at least some security bound of them lock on your particular object such that no conflicting object could ever get through. And then if you send multiple, you basically get stuck because everyone's they're locked on different items. And then I believe every epoch, they basically drop the locks during reconfiguration. Is that correct? Yeah.
That's perfectly correct. So you can almost think of this is like two-step process, the Fastpay, the way it works. The first round is you acquire a lock of certain object, and then the second round is when you share the certificate saying, hey, I have enough people that have said that I can actually acquire this lock, so please execute my thing. And then depending on if it's payments or if you want to add gas, you get the certificate of that back. And if you try to acquire locks for two different objects at the same time for the same index, then essentially you don't get enough attestations. So with this 2f+1 quorum, you have an intersection of f+1 where you need more than f parties to double sign, and that is where this standard quorum intersection argument.
That's where we need big pictures to explain the concentric circles. But yeah, generally speaking,
exactly.
Yeah, the idea is that you can screw yourself over, but as long as you're acting honest, and the network is healthy, you should get certificates that your data will be included at some point in consensus long before it is. And people should at least give some credence to the validity of those certificates, given all the validators are locked in some way.
Exactly.
Yeah. I've always looked at that protocol and been like, it's crazy how many mechanisms they have connected into the same consensus flow, which is like you have this pre-consensus component where every user can do this, or you can send it into consensus and then it reconciles those things.
Yeah.
And every time I look at that, I'm just like, it's impressive that they've been able to build that out. Yeah.
At least you can visualize it and you can look at it in the same thing. Look at Ethereum. Nobody understands Ethereum as a whole.
Sure.
I have never met I don't even know if Vitalik understands the whole of Ethereum, all the subsystems that it has. And
I'll let you make that claim. I'm not going to say anything like that.
Maybe I shouldn't have said it on a podcast, but I'm saying that I have been working in Ethereum for so long, and I've been looking at the consensus. I was working in light clients. It's just so many subsystems out there that are just glued together and it's crazy.
I think there's that book in Ethereum that I've been heavily utilizing to keep up to date, and I think it's already 2 hard forks behind. It's called the Ethereum book. Have you seen this? It's from I think Ben Eddington. I think that's his last name.
He
Unbelievable
spec, right? And then converted it into a book. Is that the guy? The guy who's writing the annotated spec?
I think so. I mean, I don't know this person. I've just been an admirer from afar, and so just have always loved this like website that has like in detail all like the way that they do aggregation and consensus in very particular ways. Because I don't think people even understand. This is going to be a long digression if we go down this road, but like the sync committee component and how that's utilized, and then like you can build different light clients with that, and then what it does and doesn't do, and like if we have ZK of the consensus layer, how that changes a lot of different things, but. My hot take is we want ZK of consensus. We don't want ZK of execution. But
yeah,
whatever.
That's an interesting hot topic to go into. By the way, we built. I think I don't know if you know about Kevlar, but Kevlar was before Helios, and it was the first light client that actually used the whole sync committee business. So I was probably one of the first ones to like look into that and then find some.
It's so I mean, I just think people get so excited about this whole like, oh yeah, the execution layer is going to be ZK5, which is great for rollups. Don't get me wrong, but the actual network, I don't understand why it's useful, because like you just want a ZK tells you that something is valid, but it doesn't tell you which is valid.
Exactly.
And like you as a user, like to actually utilize the network, you want to know which is valid, and by implication, like unless something is deeply broken, that is also going to be valid execution.
I agree with you so much, because it's like I almost think of like ZK as just a compressor. Like you had data compressors, now you have computation compressor. That's all it gives you. Nothing less, nothing more. Everything else you have to still build on top. So let's just treat it as a compressor and nothing more.
Yeah. So because like I think you have this whole thing now where like a lot of people want to build on Ethereum, but the way that they have to do it is you have to have all participants like run some node or set of nodes to like actually query the data, because you don't want them just hook it up to Infura or something like that. And if we just had like a proof of the consensus construction, you from that could then prove arbitrary things about state, and like, it'd be great. And it's just we need some BLS precompiles inside of the Stark circuits, but I think they're coming. They may just have arrived as well. So I got my fingers crossed that
we've been waiting for that forever, because you also need that to verify port certificates back.
Interesting.
Yeah, we have.
Because you guys don't have signatures over the same data, so like it's helpful to have like we can get into that.
With extra round, you can actually aggregate it. So the first round is not aggregatable because you have different timestamps.
The timestamps,
You can do an additional round and then get it aggregated. But anyways, rolling back.
We'll get there. Yeah. All right. So you get to the Sui Luchers thing. You look into it and you're like, we don't want the other half. Like we don't want the consensus part that like brings everything together. Or did you think something else?
I think the idea is to kind of flip the thing around and say the base layer should not provide you with any kind of ordering. The base layer could be much simpler, could be just giving you this very like high safety and be much more decentralized, and can be like, can do a lot of things, can do fast payments, can do other not like commutative operations. And then you can build ordering gadgets on top. So you can allow for people to say, okay, I have the shared state where I need ordering, and that's when you can like plug in your own consensus. This is some stuff that is not mentioned in the pod paper yet. So maybe I should take a step back and tell what is the difference on the pod paper and the new ideas that are introduced in the pod paper.
Yeah, go ahead.
And then I can tell you, I can connect it with the vision and where it's going. On the pod paper, essentially, what we look into is this notion of generalized consensus, and what it means is you don't have. So in traditional consensus, the way to think about it is you have this pipe, right? You have transactions coming in, and on the output, what you get is a fully ordered set of transactions. So an easy way to think is every transaction has a incrementing unique index, right? And this is all consensus does, right? Once you have this ordering, you can take any deterministic VM and kind of just execute and go on. That stuff we were already earlier kind of.
Yep. And the side note there is a lot of people now, because if you have agreement over the bytes, you should have agreement over execution, now break out the execution to be unrelated into the actual consensus process, because it doesn't actually need to do anything if everyone has the same byte stream. But sorry, go ahead.
Exactly. So this is the idea of the lazy chains by Mustafa and the whole Celestia guys. But it's been that's the kind of way to separate consensus and execution. And consensus is the ordering, achieving this global order is the expensive part. Is quite expensive on the network, because you have to do quadratic amount of communication. So you have all-to-all communication of several rounds. And we've seen again and again that it bottlenecks, it chokes, and it doesn't scale. So you look at most of the blockchains that are out there, and they cannot handle more than 100 active validator set. Maybe we are fine with that. Maybe we want more decentralization. It's a question.
These days we're talking like 15 or 16 more, not 100, but yeah, it used to be 100. But go
I'm saying that
it's less than a lot. I think that's the important part. Yeah.
Yeah, but like at least let's not have one centralized, sequencer like L2s operate today. At least let's go to, in the orders of tens and maybe even more. Why not if we can? And so that's how you think about consensus. But then what Pod is saying is, what if we allow for these transactions to like wiggle around a little bit? So people don't have an agreement on the total order, but what they see, so every replica or every party in the system has 3 timestamps associated to every transaction: a confirmed timestamp, a minimum timestamp, and maximum timestamp. And the system guarantees that my confirmed timestamp is within the min and max of everybody else's view, and everybody else's confirmed timestamp is within the min and max of my view. So it's kind of like you can think of transaction as wiggling around. And
this is like the novel part when I was reading the paper the first time, where I was like, I have not seen anything quite like this before in this type of system. So I think maybe talking very specifically about like what we're talking about, what is the min, what is the max, where does it come from, would be really good. Yeah.
Right. I can give a little bit of kind of intuition of how that comes.
Yeah.
So let's look at a simple setting, right, to just see how these timestamps are generated. So for now, we have a fixed set of validators. You can just think of these computers, running around the world. We can say there's like, 20 validators, right? And then I'm a client, and I want to write to these validators. What I do, the write process is very simple. I just take whatever I want to write, message, I sign it, and I send it to these validators. What these validators do is they look at their local log, see that this is the unique thing that they're signing, and then basically assign a timestamp, a local clock timestamp that they have, and then send me back the timestamp. And you collect a bunch of these timestamps from the validators, and then you're done. So what you get in the end is you have a certificate where you have a bunch of attestation from this given set of validators, and each certificate has some timestamp associated to it. Now, you have some assumption that part of this validator set is honest, right? So at most, certain F can be malicious. And then when you look at these timestamps, and then you can, based on these timestamps, you can arrange them, you can first order them, and then you can argue what is the confirmed timestamp and what is your min and max timestamp. So let's take a simple case here, right? In this case, if you just look at the median timestamp, right, with less than, let's say, so Pod paper is written in like less than 1/5. So if you just look at the median timestamp here, the median timestamp will already lie between 2 honest timestamps. And then you can do some tricks to find the min and the max, essentially. Does that kind of give a little bit of intuition?
Yeah, I think that the idea is that usually these systems, like the examples I've seen, were like for the case of Stewie, right? Is you send out some message and people sign it. And the idea is you want everyone to sign the same message so that you can aggregate things together and do like a succinct certificate, not ZK, or could be ZK, but generally not ZK. And then you pass that certificate back to the network. But if everyone signs something slightly different, as in the case here where they're signing a timestamp of when they saw it or committed to it, or I don't know if commit's the right word. You got to be careful with that word in all these conversations. So whatever, they sign something with a timestamp and they get it back to you, you're going to get a bunch of different signatures with different timestamps. And so the reason why that is interesting, and this is where I'll let you continue, was like how or why like that timestamp or what those timestamps can be used for. Because usually, you don't have those. And so you could send out a transaction for something that could have happened in the past, could have happened in the future. You have no idea when it could have happened on the network. And as a result, like usually when you talk about this in the terms of like a DAG or something like that, the breadth of the DAG is unbounded because you don't know what the edge or like the tip of like the graph of payments is at a particular time. And so it makes it really difficult to sync it or scale it or whatever, because like you got to sync to edges of the good. This is another big diversion. But in any case, this is really interesting part of it. So I would love to understand, if you want to continue from that point around, like what the timestamps are and what they're used for.
Yeah. So thanks for the summary. So once you have these timestamps, right, you have attestations on the same message and these additional timestamps. You do lose aggregation. We can come later how we can build aggregation on top. But what you get is you get these timestamps, and you know that most of them will be from honest parties, and there could be some adversarial ones. And once you order them, you know that the adversary cannot tip the median towards like being completely off, right? So even if it has everything set to 0 or everything set to infinity, you would still have the median being honest. And then essentially the min and max is where you allow not just the validator to have sent you a wrong timestamp, but might be saying different timestamps. So you the time range that you have, you say some part of them might actually be double signing and saying some other timestamp. So you set that part to be 0. So the worst case, that can be 0 in case of when you're calculating maximum, and it can be infinity when you calculate minimum. And you see, if you try to tip everything to one side for at most f, what is the median do you get? And that is kind of gives you the min and max. So kind of the worst case scenarios. And that ensures that your median is within the min and max time range of everybody else's view, and vice versa.
Very interesting. Yeah, I mean, I think there's some math tricks there in terms of like bounds on like what the value could worst be, right? In like a case, exactly. And that's where maybe you want to talk a bit about like where that you mentioned that the paper differs from like kind of what you guys are implementing. Does it have to do with some of the security bounds stuff that you guys were talking about, or is that staying the same? Or like maybe you can talk about where it's going, because I know maybe the first thing we can touch on real briefly though is most papers are written with this notion that like the participants is 3f+1, where f can be Byzantine or faulty. And I believe, if I'm not mistaken, your guys, the pod work is written with 5f+1, where f can be faulty. Maybe you want to talk about where that all comes from.
Yeah. So the 5f+1 is especially interesting for these timestamps to ensure that the timestamps are the median lies in the honest range. But not all of the properties actually need 5f+1. Some of the properties are actually fine with 3f+1. And in fact, we have a proof with where if the validators are only under crash false, then you can work with 3f+1. So hint, if you run, for example, all of these validators with a T, then you take the crash false system to BFT while still ensuring 3f+1. Not something that we've implemented now, but what I was going to get to is, as a principle, one of the principle of pod network is to allow for flexibility. And this is something that we will be releasing more about, but we have a little bit on our website where different clients can even have different beliefs about the system. So if I'm not using a certain property, I don't even need to assume a higher threshold resilience. The RPCs actually allow you to configure the quorum requirements that you need on your certificate. And then these clients can cooperate without needing to kind of having these hard-coded parameters on the network. And you could have even systems where some party believes in a TE assumption, so it's fine having a 2/3 crash fault resilience, while other party believes in the full Byzantine and waits for 4/5. This is something that's also kind of, comes from recent works by some of the scientists that we worked with on the flexible consensus side. We can go.
I'm very curious, like how you kind of get some sort of. Basically, the high-level question is, as a user, because that's what eventually this all comes back to, is like, how do you get certainty in that model of like what certificate you have is valid or whatever, right? Because like, if usually I think the intuition would be your security drops to the lowest common denominator, not that like there's additional usage. Is the idea that you have like different sets of people operating at different like kind of security parameterizations, then you take like some M of n of like those different like layered security configurations to get some sort of assurance that you care about, or is it something else? I'd love to go into that topic.
So essentially what we're saying is this kind of adversarial threshold is a client parameter, and it's not a global configuration of the system. So the difference is, I can, as a local client, I can say that I assume that the network has 2/3 resilience or 4/5 resilience, and I will enjoy the benefits of that. So I will accept certificates which show me 4/5, and I will reject everything that shows me anything less. And if I were believe on 2/3, then I will only accept 2/3. And what we're saying is these clients can cooperate, and the network doesn't restrict you, right? So if my assumption is wrong, then then I can have a safety violation. But I can do this kind of adaptivity where I say I want more safety or I want more liveness, right? I might be clients which are doing micropayments, and I really care about low latency and high liveness, but I'm okay if I lose safety once in a while. So I might be okay even having like 97% resilience or trusting a little bit of TEs. And then I might be clients which are selling, okay, above 100K cars, and then they can say, okay, I will really go for like 2/3 or 4/5, right? So it's kind of.
So is the idea then that there isn't actually like one validator set, or is the idea that there is one validator set, but then you just have different assumptions based on like how you end up getting those certificates, and it's up to the user to decide, or like the user of them, how to actually interpret those signatures, I guess, in some way that matters to them.
One way to kind of draw a parallel is like when you look at the confirmations on like Bitcoin, right? So if you look at a proof of work confirmation, it's a parameter of a client to choose whether I wait for 4 blocks, 5 blocks, 10 blocks, or 50 blocks, based on like how much do I want to like tolerate the fork, right?
Right now it's set to 2, I believe, right? Is what most exchanges are. I think on Bitcoin. Yeah.
I don't remember actually. I think it's 5.
It was 6 for a long time, and then I think recently, in the last 18 months, it dropped. Like someone did some math and they brought it down even further, and I don't know, or you know.
I mean, I would be scared of the whole selfish mining attacks and so on, especially too low for me. For like, you know, I build the block and I just keep it with me, and then like just try to get the second block, and then reorg the whole.
Coinbase's help page, Bitcoin 2 confirmations.
Yeah.
So,
anyways, I think we should come back to the difference on the part. I mean, this is one of the key ideas, right, on the whole timing and how do you build this generalized consensus. But if you look at more like broader parts vision and what we're building at the moment, is we want to get to this like base layer, right, which is asynchronous. So transactions do not have an ordering. You can build CRDT like structures, of course, and you can do payments, you can do auctions, decentralized socials, a lot of things that decentralized networks are used for. And for these things, you can really achieve like 1 network round trip latency or 1.5, which is like very fast, almost matching what you're experiencing with existing Web2 systems, right? Like instant. And then what you can say is applications that need ordering, and we can talk about which applications need ordering and which don't, can then choose to build their own ordering gadgets where you have lower safety, but you still rely on the base layer for safety, but you only rely on these ordering gadgets for liveness. And then what you can do is you can still use the base layer for composability. So you can still use token transfers on the base layer.
Got it. So, I mean, the idea is that, so it's kind of like you want to have this low level thing that just is about making sure any transaction that wants to be well disseminated through the network can be, and then you have some idea of its min and max time that it actually existed. And for there, the argument is that basically you can build all sorts of stuff on top of that, however you want to. Got it. Interesting. Yeah, the one. Maybe you want to talk about some of that 1 round trip latency. I know that like some people have started to post these dashboards of like different latencies for transaction inclusion and all sorts of stuff like that. I feel like most people target anything below a second, and 1 round trip is obviously much less than 1 second. But the idea is to mimic or like kind of not mimic, but mirror the experiences people are typically used to, which is 1 round trip with the server, typically somewhere in Web2.
I think it's important to maybe like even ask the question, what does it even mean to have transaction finality, right? Because a lot of these latencies, especially for L2s, they claim to be like super low. And sometimes they're not even counting the network latency. They're just counting the latency of executing the things locally. in a single centralized server. And my claim, like, that is not really the latency of the system.
Yep.
In fact, if you look at the L2 latency, it's higher than the L1 latency, right? In traditional, because you don't have any guarantees from the sequencer on your transaction finality unless you really checkpoint the thing out. It's almost kind of, you're increasing the throughput of execution by sharding stuff, but your latency, you're paying at the cost of latency because you have to still finalize it like once in a while to Ethereum, right? By posting the data, not wait for the fraud proof, but at least for posting the data, you have to wait for L1 finality.
There's no way it can be as fast as L1 finality because there's naturally this like seconds, like they're collecting it first and then it must go. So it can't, and you have to wait for that even to be included to have some notion of that. Yeah, I mean, I think the users, like an average person's understanding of the finality of the systems they're interacting with is just, there's a big gap between, I think, what people feel like it is and then what it actually is. And I think, I've always wrestled with this because it's like, is AWS and like all these infrastructure providers just a lot better and like safer than people think? Or like, is usually the rationale for this is, well, you care about that because things can get reverted prior to that point in some way that's going to derail your understanding or usage of the application. But it's very interesting that it just doesn't happen. And like, at least if it did more often, people would complain about that component. So this is an interesting like technical dilemma. I mean, I'm not advocating for the side of like, let's have servers everywhere.
The question here is, it's like, it's not happening because it's not decentralized, right? I can run an AWS server, a single server, and if that is capable of everything, then as long as that thing is safe and I trust that, it's going to be fine. The moment you even scale it, you want to at least make it crash fault tolerant. But then if you let public access and anybody can run a server, I don't really know.
It all breaks. Yeah.
Exactly. It will break down, right? Like people will intentionally write code that will take it down.
Yeah, I think the one learning that most people don't, or one nuance that most people don't appreciate when they're trying to launch like their own application or network for the first time is like the code you ship is often not the code you see on the network.
Yeah.
And so debugging it or like trying to understand like the behavior of it sometimes can be quite a different experience than maybe what you think should happen based on the code you shipped. And yeah, I mean, the problem with all these, like these, I don't know, the topic that comes up with all these decentralized sequencer conversations is it just very quickly turns into a small consensus set. And then you're like, well, maybe we should have more people that keep it safe. It's like, well, now we're just back at consensus again. So yeah, I think it's yeah, I mean, it's interesting to think about how much finality ends up mattering to people in this way, and like whether or not like a single server, if it means no one can take my money but they can censor me or like give me bad pre-confirmations, drives the decision making. But like if you want it as a credibly neutral thing, which I would much rather run as like an actual decentralized system because I don't want to be the one in charge of running that server for sure. What can you do? And I think that's a lot where these kind of ideas come from, is like, well, if you were going to try and preserve latency that felt like a single server, you probably wouldn't put consensus in there, or that's at least the idea. And the idea is instead have these nodes, have some trust around them, or like have some sort of safety bounds, but don't have them actually run a traditional quadratic communication between each other or like some sort of traditional consensus mechanism. And so, yeah, I think so let's get back to that kind of story around like how things are developing from there. So you've talked about the pod paper, you've talked about some of the stuff you guys are now working on. And so where is that now working on? So like, what are the types of applications that you imagine people are going to start to play with this thing? Because it obviously isn't as, I think the whole point, right, is that without total order, like it can't do as much, but the claim is that you can build total order on top of it and benefit from all this pre-consensus work.
Exactly. So the claim would be that a subset of applications which blockchains are mostly used for will get extremely fast, and the other subset will probably not be very fast, but will still be as fast as the existing systems out there. So the fastest consensus that you know of already. So what we have now in like the kind of applications that we imagine people building is look at applications which do not strictly rely on ordering, or look at applications where you can convert them from relying on ordering to not relying on ordering. So let's start with the easier ones, right? So payments, we already touched upon it, right? If I pay money to you or if somebody else pays money to somebody else, it's a completely independent transaction, right? So that's very easy to see. Then the other one is social networks, right? Social networks are very CRDT like. It's really a feed layer where things are just posting. There is very little conflicts because I'm only interacting with my things and I'm posting something that people can just access.
And conflicts there would be like, you know, your post doesn't conflict with my post if we post
Exactly.
at the same time. That's the idea, right? Yeah.
Exactly. So any kind of decentralized social, it's an obvious choice. You would get same kind of latency as Twitter while being decentralized and pressing the default order. Then let's look at auctions. Auctions is a very interesting case. It's like a set of things, right? Within the set, you don't need ordering, and you're bounding it with time. So you say, I want to collect as many items as I can until a certain time. And then to kind of bound it with time, you have this notion of past perfection, which was introduced in the pod paper. We can go more technical if you want later on that, which says this is my set of things I can see. And then auctions is actually very interesting primitive, right? Because a lot of things are auctions if you look at it, right? So you can start. I mean, the MEV pipeline is an auction, right?
Some would say that existing L1s with consensus are not great at running auctions. So it's an interesting claim to say this is even potentially better for auctions, because that's usually.
I mean, we wrote a blog that auctions need a new home, or was it called auctions need a new home or something like? Yeah, auctions are not a good fit for auctions. So maybe you wrote our blog, but it's like auctions, like basically blockchains are very bad for auctions. Part of the reason is auctions require very good censorship resistance, and any kind of leader-based consensus is bad with kind of censorship resistance. And then you need this set-like properties without needing like quadratic communication and so on. So pod is good for that. And then you can take, like, for example, dexes. So you can take like AMM style DEX and then convert it into like batch auctions. So if you've heard of cow swap, what it does is you have people's limit orders, and then you do an auction where you allow people to propose solutions to kind of find coincidence of wants, and it is like a Dutch auction. And this kind of converts something which is kind of very order dependent. So in an AMM, every transaction really depends on every previous transaction. Something which becomes less order dependent because now it's just a batch that you kind of settle as an auction. So that's an example of how you would take something which is order dependent to being not order dependent. So any kind of marketplace essentially is an auction, right? So like we can think of proof markets. We have some proof markets already building on top of us as a very good use case. And then like fast games. So we were also talking with like real-time fast games, real-time collaborative softwares that want to be decentralized. We have an internal version of Minecraft running on pod. Something that's going to come out.
A little vibe coding you guys did on the side, or where did that come from?
It was before the vibe coding was famous, but it was kind of vibe coding.
Oh, sure, yeah.
Where we started, build like okay, what can we test with this? And we want something cool, so we might actually release this soonish to like allow people to just kind of play and feel what like 200 millisecond latency on a resilient system feels like. So some cool applications on top of my mind.
I guess it's interesting because like I think when people look at some of the work you guys have put out, they say, oh, okay, you guys are betting that there's a huge class of applications that don't actually require total ordering. And then what you're actually saying is no. Like we think of total ordering as a superset of the capability that like applications need. And if you don't, you shouldn't be burdened by like the operations and mechanisms that get you there, and that there are these applications that can bypass it. I feel like I mean, I think with like the Lucha stuff, Sui has also been trying to make this case for some period of time that there are a ton of different things you could do that don't actually require like the full consensus state to do something productive. Interesting.
Yeah, that's exactly what we're
So
thinking.
okay. So as we're going through the system now, you mentioned there was this word in there, perfect time or past perfect time. What is that?
Yeah, it's a notion that was also introduced in the Pot paper, very recent, and we're still trying to get a grasp of all the things that we can do with it. But one of the things that it on the intuition, what it provides you is it gives you a guarantee that this is the maximal set of transactions that can be confirmed with a timestamp before a certain deadline. So when I say a time became past perfect, I know that this is really everything I can see before a certain timestamp. And this is kind of also similar timestamp trick with medians and so on, that you know that every new transaction that you haven't seen will actually have a confirmed timestamp which is bigger than the past perfect time. And this is very important for auctions, right? So if you think about auctions, what you really care about is this way of saying, okay, now my auction is concluded. Now this is a set of transactions I can see, and everything that's new will kind of not be part of this auction, right? Everything that I've not seen will not be part of this auction.
So you're trying to really bound like the max time in that bounds you shared earlier, like what all the transactions that could be at that max time or greater, assuming that you've pulled from everyone like these like kind of replicas, all the data that they have. So maybe we can go into like some of that mechanism component around like what that actually ends up looking like, because I guess here's the setting the stage, right? Like, so someone looking at this thing, they're like, cool, they read the paper, replicas don't communicate at all. And so now I'm some user and I'm like, I'm going to play a little game with this auction. And so I'm going to slowly send my transaction to each validator over time. So every 5 minutes, I'm going to send it to an additional validator. And eventually I will get one of these certificates if I continue to send it. And I get this like really long min max range. So how does that actually is that obviously that's something that the system tolerates, but the idea is that you have these indexers of some variety, or like the read components that actually like get the data from all of these replicas that don't communicate to each other, or like how does this actually get out to everybody? Because I think that's the big question, which is like, I can't just run a node, right? Like I have to somehow now interact with these nodes of some.
Let me tell you how the system operates. So we have this paradigm which we call as streaming. So you don't really fetch all the data all the time. You really subscribe to the interesting data that you're interested in. So the Pot paper itself probably describes it in the say that there's only one protocol running one auction and then you're running it, but you could just connect and say, I am interested in this particular auction, and then just be subscribed to that part of the data, right? So what's happening is, let's say I'm subscribed to an auction, right? So I'm a bidder, I'm subscribed to an auction. I send my bid, right? And I say, keep sending me everything that's related to this particular auction. And I also want you to send me a timestamp when the deadline has been ended, right? And then what happens is I keep receiving these attestations. And as I receive these attestations are also timestamped. So I can look at what is the last timestamp that like replicas have signed. So I have a list of timestamps that I've received, the last ones from all of the validators. And I know that validators cannot sign in the past. They can only sign in the future, right? So based on the timestamp that I've already received, I can kind of calculate what the minimum next has to be. And essentially when the deadline passes, I also get a heartbeat that updates my things. And then again, it kind of gives you this notion after some time that you have received enough attestations that you can calculate that the confirmation timestamp of the next one should at least be this one. And that gives you kind of a guarantee.
So let me see if I can summarize this, because I think this is the real meat of like how this all comes together is you have validators and they sign things that are sent to them. They sign them in their mind in a log. So which means that they have like basically assuming they're honest, like an ever increasing log with each transaction having some index.
Yeah.
You have some other mechanism that is not actually like listening for transactions, that is polling the validator's like tip of their log. So
Yeah.
like this validator 5 is at, I'll use letters here. Validator A is at 10, validator B is at 15, validator C is at 30 or whatever.
Yeah.
Doesn't matter. And if you're up to date on what that log is, you know what their last signed transaction is. And that includes a timestamp. So you know what their local clock is, assuming again that they haven't been Byzantine. And so you have some auction and you're like, okay, once, I guess in the case we've been talking about, let's just say in the setting of the 5F+1, once you have like 80% of the tips, you know then that like no things can be added with a max time that exceeds, or like if you have something that's set at a max time, you will not see any other transactions that could sit in this bound of max time. There may be transactions in progress that started before the thing, but you know that the term you use past perfect time will never can never be less than whatever your auction end timestamp is. So you won't miss anything. This is the construction, right? Or like as you think about the auction mechanics.
Yes, that's roughly the construction. And I mean, of course, you can look at the paper for exactly how that is being calculated. There's a little nuance there, but it's roughly that. So you just stream, you keep getting the timestamps, and then based on that, you have a local calculation of what anything new can be. And you have this small other addition is every transaction also has an index, so not just a timestamp but an index that you can help validators accountable, as in like if they double sign or if they sign in the past, you know that you're missing some transactions on a particular index. So that is another small mechanisms to make it accountable, censorship resistance, and then you have this past perfection. But
and accountability there for folks listening is basically saying, if I submit a transaction, validator signs at a particular index, and then someone else, you end up like syncing from whatever mechanism we're running here, and then you see someone else's transaction at that index, you're like, whoa. And so then I guess you can send that like basically both of those to everybody, and so that they know that validator is no longer honest, I guess, and then something can happen. Yeah. Very interesting. So I guess the question that becomes, so like, do users run or like are expected to run these things that poll validators, or is there like some sort of service you imagine existing that kind of provides all this information for them? Because I would imagine if you're talking about these like super low latency, high throughput systems, you don't want every user device to be polling this information. Yeah.
Right. So you can subscribe to the network and you can get like relevant application specific information. There will be what we call as relayers and like read and write gateways for clients which have limited bandwidth, right? And the key thing to note here about gateways is you don't rely on them for safety, you only rely on them for liveness. So, if a gateway shows you a particular certificate, you can verify it locally and it's fine. But the gateway cannot, gateway can only censor your transactions, and you can switch to sending everything on your own.
So you may not know, like you may miss some transaction related to your application. Like you have no way to prove that everything has been sent to you related to your application. Or
no, you can. You do. So the pass perfection is a certificate. You can give me a pass perfect certificate on a set, and I know that this set is complete. Correct. Yes, it's complete. You cannot miss out something, but you cannot. I can send you a transaction and you just censor it. You do not send it to the network. So that.
So can you talk a bit about how that kind of works? Because I think as we're like I feels like we're kind of putting this together from the start to finish to kind of see how it all comes together. Then we can get into some of the edge cases here. So the idea is that you so the problem, right? So like, okay, I send all this stuff. I'm running this auction. Cool. All makes sense. I'm now collecting things related to my auction. Cool. But now I'm an auctioneer and I want to do something with this information, maybe use that in a future transaction or like take it off chain and put it somewhere. How do I know that if I only subscribe to a subset of the application data that is related to my thing, that it is a complete subset, right? Because you could imagine, some indexer withholding some transaction that dramatically changed, maybe the best bid, for example, or the second best bid, or the bid of their competitor, to ensure that like the auction is manipulated in some way. And this is a problem, especially if you're trying to expose like or perform some sort of total order over the system, because now you can cause people to not agree on the contents of the auction, which will break everything that comes after. So yeah, understanding like this past perfect certificate is this where like some of the Merkle segment tree kind of stuff comes
Yes,
in, or
exactly. So I'll keep the construction simple for now and just say there's one auction running, just so that it's easier to understand. And I think there is still open questions when you have multiple applications, you just subscribe to a particular one. And the idea is actually, you can show me that this is the kind of last indexes or last timestamp ranges that the validators have signed. And then I can look at, and you can provide me kind of a set of attestations on the previous ones, and then I know that I'm not missing any of the indexes. So this should be my set, right? So you provide me with all the relevant information on, okay, this is the timestamps, attestation on the timestamps that kind of give you a maximum, that the time has been passed, and also that these are the last indexes that they've signed, and these are all of the kind of transactions that is relevant. And then if you use Merkle segment mountain ranges, then you can make this thing more succinct. And essentially there's tricks on you signing just the MMRs and then having segment trees to show that you're not missing something.
This is where it'd be interesting to have all sorts of slides and whiteboards to talk about how these things
you need to like draw it out.
But yeah, I'm not gonna ask you to use your hands too much here as we talk through this. But the idea, right, is you want some efficient way to know that for like the duration of your auction, you have everything that could have been in it, and you want to have some succinct certificate of that thing, so that you don't have to go fetch all this random shit of all these other people's applications over some period of time to understand what is in your application. Got it.
Yeah.
Interesting. Yeah, I mean, I think this approach of like basically dumbing down, I don't want to say dumbing down is not the right word, but like simplifying the protocol constructions and then relying more on the trust we get from signatures and certificates, and then using a lot of infrastructure to scale access to that seems to be like kind of the way that some of this technology is evolving to get these gains in like latency and throughput. Like I think a lot of people originally were like, at least when you talk about EVM nodes, right? It's like, oh, you want to run the RPC layer? Well, you just got to run a whole EVM node and then just put those all behind load balancers. And instead now we're seeing, I think a lot of the newer efforts and teams totally don't do that approach. And they assume that like each node or like implementation of the network knows nothing about this like infrastructure layer, and it lives externally. And then you're trying to basically enshrine something like a Merkle, what do you call it? A Merkle segment Merkle mountain range. Yeah. To like give people that are listening to this infrastructure layer the ability to quickly or efficiently verify that the infrastructure has all the stuff they need, and that the infrastructure layer could not lie to them about like the things that they're pulling from it.
Right. Instead of you executing it locally or running a full node, you get actually a certificate of the execution from the network itself, so that the light client's problem for like pod-like construction is more interesting because things are more decoupled, and you don't have to like sync to the latest kind of root of the state, because nobody actually knows the latest state root. But you just have to convince me.
Nor is there, I guess, technically. You don't know, because you can't know where everyone is at a certain point in time, right? Yeah.
So what the problem is more interesting because it's more like, I just convinced you that I paid you, right? And that's enough for you. Like, why do you care what the world state is? You only care that you received the money. And as long as I show you a quorum certificate on that, you can be fine. You don't have to know what everything else is happening around the world.
Only care about what matters to your use case or application, I guess. So yeah, so I guess like where this, I think it's super like nuanced, I guess, is like around how a network like that can adapt to like new people joining or leaving, or like where stake kind of comes into any of this? Because I mean, like the context, and you know, just for the audience who's listening, I did not prep him on any of these questions, so this is very much like a rapid fire. So appreciate your willingness, and so all this is active research, I'm sure. But like the idea that if you don't have the network have some notion of like what its current state is, how can you understand like what the current stake weights are or something like that? I guess you can basically build in some sort of bound on like the past perfect time of some like stake contract and then utilize that in some way. Very curious if you guys have thought about that and whatever, because I mean, I guess like the layman's go ahead. Yeah.
Very, very good question, and a lot of relevant things that we are discussing. And as you said, like these things are not fully final for us.
Yeah.
We are like taking a more progressive approach of building some network out and getting adoption, and while we decentralize and make it more open. But we do have some very good ideas on how we can do it. So the trivial approach that would work is you can just have kind of one sort of reconfiguration chain, right? Which is okay, I use this chain which has consensus, which is just responsible for reconfiguration, right? And it doesn't block transaction. It doesn't mean that all your transaction will go through that. You just refer to that reconfiguration chain for stake distribution, right? When the stake is committed and so on. So that is the easy solution that we know would work. You rely on Ethereum or some other network, or could build your own. So let's eliminate that for now to entertain more interesting constructions and see what we can do. So there is this paper which is called ABC, or Proof of Stake Without Consensus. And that actually talks about even stake transfers in the fast path. Because you think about the stake transfers, it's really token transfers. And as long as you have some guarantees on the balances, and then you can get a quorum on the stake transfers and so on. So it doesn't talk about like kind of electing a smaller subset committee. So you get like a quorum on the full stake, right? Everybody's stake. So this might get slower, though it talks about delegating stakes. So people can delegate stakes, and then you can get a bound on your balances, and then as long as you get sufficient quorums, you're fine. So you can keep moving without like kind of, you don't need kind of like reconfiguration also happens in the asynchronous fast path, right? But then that is not sufficient, right? Like if you want to make it more optimized, you want somehow to allow for like maybe a smaller subcommittee to be selected. And to allow for like the subcommittee selection, you need on-chain randomness. And this is something we're looking into. We don't have a construction yet there, but the idea would be you would have this asynchronous path also be able to generate on-chain randomness, and then you have maybe some ways to bound that randomness and how much it can be biased by the adversary, and then apply that to this thing to be able to select a subcommittee. That's the direction we're trying to get to. We have some ideas, some rough instructions.
The pain is always like you get the for people that maybe are not as familiar with like the way a lot of these consensus papers are written, they're almost always written these days in some notion of what is called like a permissioned system. So there is some set of people that are currently participating in the protocol, and there's no conversation about where they came from or where they go. It's just, this is what it is now, and the network can be good or bad, and as long as these things happen, it's all good. And the problem we're referring to here is what we call like reconfiguration, which is this natural thing that any proof of stake system has to add to these consensus protocols, which is to say, cool, what if like that staker goes offline, or like we want to slash them? What if they want to unstake and take their funds out of the network? What if someone new wants to join? And there's this problem with how you basically allow that to happen if you want to ensure that you still get consensus in each particular point. So like if you have people that are out of sync, you can halt the chain by accident. So like I'm more familiar with this in the traditional consensus context, right? Where it's like, okay, let's say that you swap half the network. You probably wouldn't want to do that for a lot of different reasons, but let's just say that happened. Well, you could have this fork almost that goes both ways, where like in each fork of each other, the new participants almost act like a Byzantine adversary that is greater than like the bounds of the network. And so then you actually have the chain go different directions based on who or what is considered as like a valid certificate or like aggregated signature for a particular view, and the things can diverge. And so the reason why this matters for something like what we've discussed here already is, you have these validator logs that you're basing all of the auction information on. And so incorporating the logic of like how if a validator is added, how does that change the dynamics of the auction? Because now you may need to know about new validator logs, or like not consider parts of one validator log if they're no longer part of the active set. And so, yeah, it's always the fun part that comes after that. You like get it all to work and you're like, well, fuck, now we really gotta get it to work.
I think the approach we're like taking at the moment is to like say we will just like start as a AVS or a restake protocol where we just rely on Ethereum for the stake distribution, so that we can push down the problem for a little bit later, and start with something that people can already start using and get all the good stuff.
Yep.
And then build on top and see if we can like slowly allow for like making it itself a completely sovereign network, right? So we get a little bit more time, and also we don't need to launch any kind of token or anything just to start. It helps to be relying on Ethereum.
Right away. And then we can, and like just like that, we come back to the consensus layer proofs that would be super, super useful for something like this. If anyone's listening, this has actually been a very common thing we've noticed too. Is like the first goal of many teams is not to like figure out how to like bake arbitrary reconfiguration into anything. Instead, they actually want the exact opposite. So like if the chain is entirely unaware of reconfiguration, and instead it can like work with different sorts of seeds of like views, or like we'll call it just epochs for the sake of this conversation, where like the participants are something at a certain point, it dramatically simplifies everything that you're actually building on top to make sure it even is something people would want to stake on if it did exist. And we've found that to be a very common approach these days. Is like if you can pull security from other places, very commonly ETH, you can kind of avoid a lot of this protocol complexity to get some sort of application off the ground to begin with, and then start to work on all these different dimensions around actually making it a standalone thing, which has to deal with these problems. Yeah, that's a tough one for sure. Yeah. So I guess, I mean, the last question I kind of wanted to discuss here is, I think when a lot of people see these sort of systems, they seem too good to like, be true. Like, is there some issue that's going to come up later on the line that changes it, right? Because like in the case it works, it's really, really fast, like way faster than anything most people can interact with today. And so it would be great, given your background, like more of the technical side of things, to maybe talk about some of the specific trade-offs you guys are making around this, so that it's not just like, oh, no, we skipped over all these impossibility results, we just found like a better way. It is instead more of a conversation of, no, we are making very particular choices around how these things come together to give you this feeling of latency, because there is no, as we know very well, free lunch in how you design these systems.
Yeah, certainly. I think if you look at the class of problems the blockchains are solving, right? Currently, everything is paying the cost of global synchronization. Everything is paying the cost of consensus. And the trade-off that we are making is things that do not really care about ordering will not pay the cost. And when I say ordering, it really means like if things are not dependent on one another. And you can already think about applications, right? Applications, even if they're interacting with one another, they might be dependent, but they can be completely independent, and they should not be. If my application is congested, it should not congest your application, right? So that's the easy way to think. But also, a lot of things, like we talked about payments a lot previously, right? Stable coins is one of the key use cases that we've seen on blockchains, right?
Sure.
That now has a potential of mainstream adoption with the similar kind of latency of Web2 systems, and this can live on pod and have these good stuff. Of course, if you look at Uniswap as it is today, right, which requires really everything is dependent on one another, would not enjoy all the benefits. Though, if Uniswap is congested, it would not congest your NFT platform if it's not interacting with Uniswap, right? So it is a trade-off that you make, and you will. Composability would be an interesting question that we did not go here, but we have some very interesting ideas of how you would compose between the fast path and slow path and these ordering gadgets. But we have a very interesting way of doing it.
If there's anything you want to share, I'm all ears, because I think people like, I mean, because this to me is like the natural. Yeah, that'd be great. Yeah, because I mean, the brief allude here, right, is exactly what you're talking about. Is if you have these like one-off things that can be locked or like agreed upon, what if you, I don't know, like in the case of DeFi, want to do some sort of like flash loan concept or like something where you have different transactions interact? So yeah,
flash loan is a very interesting edge case, right? Yeah. Which is like two applications being dependent on one another. So let's start with the base, right? The base layer is you can do fast payments and commutative operations, right? Like feed layer style, auction style. Yeah. And then we say, let's allow people to build ordering gadgets, right? So, Uniswap said, now we will deploy a Uniswap contract. We need some ordering for certain state. The only thing they will do is assign indexes, right? They will not be executing. The base layer still executes, right? So there is no fraud proof window and so on. What the ordering gadget is doing is it's assigning indexes. So this transaction is index I, this is I plus 1, and so on, right? And then the base layer still does all the execution. And then you can have different applications that have their own ordering gadgets. The ordering gadget could be a centralized sequencer, like we have for L2s, or it could be a consensus protocols. Could also use the pod validator set, more enshrined and native if you want to. And then now let's think about composability here, right? So we want the accounts to not live on the L2s. The accounts are still on pod. And then if I do a token transfer, if I transfer money, then this is still supported on pod on the base layer. So I don't have to wait for synchronization of the ordering gadget. I can transfer tokens to this application. The application can transfer tokens out to another application or an account. So that is fine, right? That doesn't need synchronization. The other interesting thing is when you have two applications that are talking to each other, and that comes in very few cases where you have things like exactly flash loans, right? Where I have to kind of wait for the other application to tell me if the things happen correctly and come back. And that is when you open like a state channel between these two things. So you have to have this cost of synchronization between these two ordering gadgets. But the interesting thing that, just to roll back a little bit, is these application specific ordering gadgets, they do not break the safety of the application. So if they start kind of double signing things, the application is still safe because the network ensures that you cannot get a transaction to have attestations on two different indexes. So safety is still ensured by the base layer, while it can only use the liveness partially. And it can have ways to recover if the thing is back again. I might have said a lot of things, and maybe you want to like break it down, Patrick, because you're much better at breaking
I think that. So I mean, some people ask, like, and this is a good framing to kind of the summary is like, are you? Because I don't know. Over the years, it feels like there's been this weird like maximalism around certain consensus constructions, and like it makes absolutely no sense to me because it's like they always evolve. Like usually people come with better ideas over time, and the idea that like you're a maximalist about like a protocol spec is a wild idea to me. But like to me, it's like I find it super interesting to talk about different specifications of people trying things totally outside of the realm of like kind of what we've seen before, because I, for one, definitely don't think we're anywhere close to the efficient frontier of like what is possible in blockchain on a lot of different metrics, but it's very much I think from the security perspective, it's pushed a lot of people into this world of if it ain't broken, don't fix it mentality of like, well, it's been deployed 100 times already. Like there's no chance 101th breaks or something like that. But I think it leaves a lot to be desired around like how it can actually really push applications forward. And so when I hear this, state channeling like lightning or like Raiden or like these things like that, I think the way I think about it is you only need to acquire locks on the things that are composing together. And in that world, it almost looks like this, the term in programming people use is like this actor model, right? Where you like have an actor that starts something, usually the user, let's say in this case, which then flows to different kind of parts and then eventually resolves to you. And is it going to be as fast as like the super low latency stuff if you're just on your own? No, but you're also requiring more things to be touched. And in theory, I suppose, is like with the right construction of like the execution logic in each of these steps, it should eventually come back to you. Or like come resolve itself in some state down the line as it hops across different components of this, assuming the key here being that unlike a traditional CRDT like sort of approach, there's this notion of every step cannot be like reversed via like some Sybil or like reversed via some sort of weird execution. And that if you have a stability of how the logs are actually generated in each part, you are in relation to yourself or any number of other components, and you are ensured that they will all eventually, basically that time moves forward and that like your transaction will flow across any number of things as long as it can kind of route itself through the network, or you drive it, I suppose. So I think the takeaway for me for all this has been, at least like particularly this answer too, is you can break apart more of the consensus process than people realize. And when you submit a transaction that has some fee on it, you may be paying for a lot more capability than you actually need to interact with these systems. But right now, there is not a great way to say or like interact with the system where you're like, I actually don't need all of this stuff for this type of transaction, right? It's all or nothing in the traditional consensus system. Mm-hmm. And so the idea that you can instead layer functionality based on the different types of applications on a global set, which more or less handles, I guess, like the auction component, which is already a difficult thing to do in like a traditional consensus system, is an interesting way that these things can all kind of fit together in a way where the problem of actually getting the transactions in a certain range of time is a really hard problem to actually do reliably. And so the idea that you do that just as that component, and then turns out there's you guys have found an elegant way to represent that, and then now are working on ways to layer gadgets on top given these properties underneath. Yeah. So I think usually people see it as everything in that layer is kind of just one compressed line, and it's like you can't really break it apart. And if I'm correct, please correct me if I'm wrong, is like the layers there are actually really rich and interesting to break apart. And then if you need to, given how fast things already are, you can probably recover an ordering or some of these other gadgets still really, really fast. But the things that don't need it don't need to pay for it and don't need to wait for it.
Exactly. You summarized it very well. And it's exactly like you're paying for more things than you need. And if you're a traditional Web2 dev, you might be aware of acquiring the table lock. Currently every transaction is acquiring the table lock. And why do you do that? Like, let's just acquire locks to things that you need, only pay for synchronization when you need to. And that will give us like systems which are much more scalable. Another small point I want to add, and I forgot to mention earlier, is when you allow applications to build their own ordering gadget, it also like opens up new avenues for them to capture or give back MEV, so they can decide what they want to do with their MEV because they control their own ordering. They can do options and give back users MEV. They can give it to the sequencer, whatever they want to do. It's up to them, and they can also play a little bit with how they want to do gas pricing for the shared state. So it opens up new avenues for the applications to capture the revenue. And we've been seeing so many like applications launching their own L2 just so that they can capture more revenue. Now the layer provides you to do that, which we don't have in Ethereum at the moment. So that's kind of a new also design space that we're exploring, and how to allow applications to capture this nicely, and how to allow them to program it, and maybe have some presets around this.
So I guess the crazy leap you could make with that, and you probably already have, and we're just repeating it now, but given that the inputs are known, fixed, and deterministic, you don't know exactly what time they happen, but at least you know the set. Yeah. That means that is entirely verifiable of exactly what the output of processing that set would be. And potentially then you could apply arbitrary order on top of that based on some heuristic. Let's say the example heuristic would be I have some VRF, and then I just basically order the transactions in the auction based on their hashes or something like that. So you don't care about the times, you just know that they're in this box. Because anyone could reproduce the application specific ordering in that case, you actually could just have these batches apply some sort of as you referred to earlier, compression function, or Stark or Snark, to kind of output the results of that auction. And then there would be no disagreement around this is a lot of signature verification, but I think it's possible. And be able to get a succinct representation of the processing of an auction that then could be used anywhere, because there should never be more than one way to process that set. And you should have signatures all the way down from all the validators of their tips at certain points to know with trees that everything is valid. Now, that may be a lot of different pieces to pull together, but if I'm understanding this correctly, it seems like as long as you can compute a ordering and know the total set of participants, you could really leverage a lot of these other constructions to extend the functionality, or make it easier to replay.
Small nuance that you don't have an agreement on the set, you just have enough properties to do auction, and that is you have different ways to do auctions which are optimistic, because if you have agreement on the set, then you get consensus. So when we looked at the past perfection, there could be transactions that can go out, but there's transactions that you haven't missed. So you only have one side of the equation. So
there is no min bound on where things could be included. So hear me out. So if you have a tree that has a tip that's signed, you could, not saying it's efficient enough to do this yet, but you could iterate over all the items in the tree.
Yeah.
And from that determine exactly what is in there in a particular auction, because you have everything up to the max.
Yeah.
I think. And then if you have that, you can then do some of these interesting extensions around actually proving exactly what is in the set. But if you don't have that capability, you would need to basically do an exclusion proof for every element, I think, that is not in the set, to make sure that you have the full set. You basically have to prove every element that has ever happened on a validator, I believe, to get some notion of everything that's in a particular set.
Yeah, I mean,
maybe totally off base at this point, but my understanding is if you have a full log for every validator, and that log is basically a MMR or some variant of it, if I have all of those MMRs, it wouldn't be efficient without some sort of Stark, but you'd be able to prove inclusion or exclusion of a transaction.
Yes.
And if you have that, you can then generate a proof of proofs, which is basically saying that this is actually the set in this auction, given this max time.
Yeah.
I think. I don't know. We'll see. There's a lot. So, I mean, this is the fun part of these new mechanisms, right? Is there's a lot to explore. So, there aren't the same mechanisms that you maybe have used to, running Block Scout or something like that, are not available to the application developer. And so there's a lot more to consider around it. So I think this is a great way to, go ahead.
By the way, we because you said blocks out, and we already have a internal DevNet with Block Explorer, Faucet, and it's EVM like. So we're not stopping on the development and making the interface very familiar to
You're
what
not stopping at the super low level. You're showing
exactly.
how things together.
We want to give people something they're familiar with and they can play with, and you'll be getting more of this out in the next days and weeks.
So this is exactly what I was going to ask. Is like, so assuming this has resonated with somebody, what should they do? Like, oh, cool, I understand this construction. Should I read the paper 5 more times to make sure I get it, or should they come out to you, or like what? How do you recommend people get started if they want to learn more?
First of all, if you resonated, you liked it, definitely reach out to me if you have questions. But we will be releasing our early DevNet. It's going to be buggy, hacky, very early, but it'll have a wallet, explorer, faucet, everything, right? It's going to be very much EVM like, and we will have some fun applications on top. I already gave some hints in the start, but we have some more fun stuff. Yeah, we would love people to try that out, give us feedback, break it, and we will keep adding features and keep iterating. So one kind of narrative that we're different from other like networks and so on, like we don't want to wait for 2 years to build something big and then be out. We'll be pushing things as we build, and we want to build with the community and get feedback, and already have applications natively built on us. So if this excited you and you already want to start building, even before we're out, reach out to me and I'll give you your early access, the private URL. But if you want to wait for a few weeks, it'll be out anyways. And yeah, try it out then.
You heard it here. There's a private URL, so if you scrape the right sites, you'll be able to find.
Somebody actually DOSed us. Somebody found the URL.
Classic.
Probably thought they would get airdrop, and just decided to.
And this is why we can't have nice things. It's as simple as that. Yeah,
But it's okay. I find fun in it, and we see the latencies and stuff. So. Yeah.
I mean, I think when people, this is just funny stories. It's like, as soon as you have such crazy incentives and momentum tied into these infrastructure layers, it's turning all these crypto people into exceptional infrastructure engineers, because the standard stuff you have, if you spin up a dumb Web 2 site or something like that, not really the same. People are going to be dosing you from all over the place, trying to figure out how to either make you look bad or try to get some sort of active benefit from it. It's a whole different dark side of their dark art of this whole space. That's very interesting to see it play out. But if you play some application online for some new blockchain application and it works really well, you should know that behind the scenes they're probably doing a whole hell of a lot of stuff to make sure it feels reliable for you, because it's a war zone out there. Yeah,
I know it working at Paraswap, and it's there's a lot of things that goes into the background to get a blockchain application work smooth.
Yeah, I mean, I think so. This is the area where at least we at Commonware have focused a lot. Is we think there's this huge appetite for primitives that you can kind of pull together in different ways to build these sort of complex new constructions. But there's always this huge chasm between those applications and then what people can actually interact with online or in their applications. And so a lot of what we're doing is around augmenting these open primitives with infrastructure pieces that you can then pull in to do these sort of standard things. So this is exactly the area where usually people fall off the cliff, which is they have something running locally, it works really well, and then as soon as they try to open it up to people, it all falls apart because they don't understand or appreciate all these different mechanisms that need to exist to ensure users are reliably served. And so we have found this to be a huge problem, and it seems to only get worse with more and more throughput and more users, especially if you're trying to show low latency. Yeah. And so, we wish you the best of luck on building that out, because it is hard stuff, complicated stuff to get right. Yeah.
Thanks a lot, and we should probably look into your stack as well and see all the tricks you've got. Maybe we have another chat on that.
It's all Rust. It's all open, so you can use it. But it's I think I mean it's been great to have you on and talk about this whole different side of how applications can be built without maybe the traditional pieces people are used to. And it's really great to see different teams taking a deeper look at kind of the mechanisms that have got us this far. And really asking good questions around, should we keep doing those things or should we swap things out? So yeah, thanks for coming on, and thanks for answering my questions here and all over tangents. But yeah, appreciate it, and thanks again. Good luck.
Thanks a lot, Patrick, for inviting me. It was fun.
See ya.
See ya.